Hi dear students, how are you doing? I hope you are doing great. Let's get started chapter 5 from grade 12, Wzary grades, and from Ishik Boys High School, Shvan Jaffer is with you. Guys, in this chapter, we're going to talk about magnetism, and we have 3 sections. Section 1, it's about the magnetic field. Section 2, it is about magnetic from electricity. Magnetic from electricity. And section 3, it is going to be about magnetic force. Now let's get started with the first section. In the first section, we have the magnetic field. First of all, this section is going to start easily, and easily is going to talk about the magnetic field, and at the beginning it's going to just talk about the magnets. And you know that for a magnet we have a poles, which is we have the end of the magnet we call it poles. We have a north pole and south pole, as you know. And the name comes from the behavior of the magnetic on the earth. If a ball magnet is suspended from its midpoint so that can swing freely its horizontal plane, in fact, a compass just a magnetic needle that swing freely on a pivot. Like poles of the magnet repel each other, unlike the poles attract each other. This is important. Unlike the pole, like poles are going to repel, and like poles are going to attract each other. And you know that for understanding much better from the magnet, we just have to draw a line which is showing the north pole and south pole. And we have a field for that magnet, which is the fields are going to, we are just going to say, for making it easier, we're going to say the fields are going to start from generating from the north to south pole, as you see, from the north to south pole, the magnetic fields. These red lines, we call them magnetic field lines, and later we're going to talk about it in detail. We have some logics, which is you should know that then the magnetic fields are going from N to S. Actually, it is not going from N to S. It is just a continuous circle which is circulating around the magnet and inside the magnet, like this one, as you see. So you can say outside of the magnetic fields are going to generate from the N to S, and inside the magnet, it is going from the S to N. This is the quick and easy way to explain the magnets, and so easy and basic. And we have superconducting magnets, which is the superconducting magnets. We can have it in extremely high temperature and plasmas that are used in a controlled nuclear fusion researches. And superconducting magnets also we can have it for levitated modern trains, which is melt train we have. Later you can search for it, are faster and provides a smoother ride than the ordinary truck system because of the absence of the friction. As you know that because we are using the magnets, one below, one at the top. In that case, there is a less friction, less sound, and the passengers feel comfortable. Again, I remind you, the like poles are going to repel each other, and unlike poles are going to attract each other. This is the quick way to explain the magnetic fields. And magnet, it has a field. So those red lines that I drew, it's the field of that magnet. In the other way, you can say it's the force of that magnet. According to those lines, it could attract the magnetized objects around it, repel them. There is a fact and the differences between the magnetic field and the electric fields. Electric charge we have and magnetic poles we have. Electric charge, they can be isolated. You can keep them inside anything you want, inside a container, inside anything you want. This is for electric charge. You can isolate them, but magnetic poles, they say magnetic fields cannot be isolated. Okay, they cannot be. So how many, no matter how many times a permanent magnet is cut, okay, you cut it, you cannot separate N and S. So you can easily look at this example. If you have an N and S, if you cut it into two parts, you cannot have N, S and N. No, never, you cannot have something like that. So always, if you cut it infinity, you cut it again, you're going to have a two pieces of magnet. One side will be N, one side will be S. If you cut it again you will have smaller pieces, which is one side N, one side S. So you cannot have only N's, you cannot have only N if you cut a magnet. Okay? Look at this Wzary question 2015. They ask section review question, by the way. When you break a magnet in half, how many poles does each piece have? When I cut this magnet to two pieces, so each piece has two poles, and S. You cannot say each piece has one poles, only two poles, okay? And then let's go for the definition of the magnetic field. As we said, magnetic field is a region in which the magnetic force can be detected. I don't know you tried in your daily life or not, but if you have a magnet, you're going to bring a piece of iron near to that magnet, is going to attract it. If you make it a bit far away from the magnet, in that case you see it's not going to attract it. So it means that it is out of the field of the magnet, it's out of the force of the magnet. And then the easiest way to detect the magnetic field lines is to use the compass. And magnitudely, the magnetic field B, capital B, we're going to use it because it is the vector quantity. It means it has a magnitude and direction. So it means we can say magnetic field negative or positive, or we can say magnetic field to the right, to the left, to the up, to the down, or to the down the page into the page, which we're going to talk about it. So the unit is so much important, guys. The unit is so much important. The unit of the magnetic field is Tesla. Okay, the unit of the magnetic field is Tesla. Capital T is going to be the symbol of the unit of the magnetic field, which comes, you can say, comes from many things, but in this section I just mentioned about this one, but later on I will mention about the many different units that you could have for Tesla in different ways. But in that case, it comes from Weber per meter square. I will explain Weber in the next page. Weber, it stands for what? Magnetic field of a bar magnet. If you have a bar magnet, how you can indicate the magnetic field? As you see from the figure, we have many compasses over there, and we have a magnet NS, and you already know that magnetic fields are going from N to S. From the up and down, still it's going from N to S. NS. And then the arrows shows us which is the magnetic field going from the N to S. Okay? Now, if you have compasses around them, you see the compasses are going to show you the direction of the magnetic field. Now, if I ask a question, in this figure, which of the following compasses are going to show us the correct direction of the magnetic field? Is it going to show us, we feel the field, we said the field is going in that direction, but it's opposite. That one cannot be, this one it cannot be, and this one is showing us to the up, which is not going to be the direction of the magnetic field. But the magnetic field is following this path, which is similar to the B, and it's entering that part south, and it's going to be the same direction. So A and B are going to show us the correct direction of the magnetic field. And you should know that the magnetic field exists within the magnet as well. Inside the magnet also we have a magnetic field, and the direction is south to north. Keep it in your mind. All the inside is south to north. We have something else which is magnetic hysteresis. Magnetic hysteresis, when you can have a magnetic hysteresis. Or what is the magnetic hysteresis? When you brought a piece of iron near to the magnet and you rub it against the magnet, in that case the magnet will apply a force on the piece of iron, and it will make the atomic dipoles of the iron to be aligned. What do we mean by the atomic dipoles? If I make it easier, I'll say the particles. It will make the particles to be aligned. Guys, if you could look at the inside of the magnet, if it is the inside of the magnet, and you will have atomic dipoles like that. If it is the magnet, all of them will be aligned in the same direction, because if it is in opposite direction or randomly aligned, randomly separated inside the piece of iron, in that case it's not going to produce any fields in the same direction or in opposite direction. Guys, look, this is going to show us the atomic dipoles. All of them are aligned. So one side of them is going to be the N, one side of them is going to be the S, which is, we name it as N and S for making it much easier. So we might say this is going to be S, this is going to be the N. But if I have a piece of iron and the dipoles are going to be aligned somehow randomly, in that case it's not going to be the magnet. How I can make it magnet? If I could apply a force over those particles, over those atomic dipoles, and by that force, if I align them like the previous example, like this example, in that case it becomes a magnet. So that's why we call them ferromagnetic. Ferromagnetic, like what? Like iron, okay, like cobalt. And by bringing this magnet near to that ferromagnet materials, it will align the atomic dipoles themselves with the field of the external magnet. If the process goes well, perfectly, even when the field is removed, the part of the alignment will be retained. The part of the effect, the part of that force will be still retained in that iron. The material has become magnetized. Okay. Now, when the material becomes magnetized, in that case, it will stay forever. It will stay. It will become a magnet forever. But sometimes it's not going to. The force is not going to be good enough for making them to be magnetized forever. After we remove the field, they will be coming back to the original shape, which is randomly organized one, randomly separated, let's say. Okay, this is the magnetic hysteresis, guys. I hope you get the idea. Now let's go for the something else, which is, let's clean this one up. Okay, and then let's go to the something we need, because we said magnetic field is vector quantity, and you already know that magnetic field is the vector quantity, velocity is the vector quantity, and the force is also a vector quantity, and the current also, it has a direction. Now in that case, in this book we're going to use some signs. You should know that this arrow, you know already, if it shows us up, it means it is in the plane of the page. It means to the north. Okay, it means positive y. But if I change the direction of the arrow, you know which direction it is. But it is not two-dimensional. It's not only x and y coordinate in this chapter we're going to study. We will have a x, y, and z coordinates. So for Z coordinate, it means one of them is going into that page, and the one is going out of that page. If I draw the coordinates, you have this one. This is going to be the positive Y and positive X, and we will have a Z coordinate in there, in that distance. That's going to be the Z coordinate. And you know already that this is going to be the positive Z. That's going to be the negative Z. So this negative Z, it means it goes into the page, into the screen. And this positive page Z, it means it comes out of the page. So in the question, sometimes it's not going to give you out of the page. Instead of out of the page, they will just write a big dot, as you see. So when they write something like this, a dot means something is coming out. So they might be a field, or they might write dots. They might be a velocity, and it might be the force and the current. It doesn't matter. The direction of the current is out of that page. What is going to be the direction of the magnetic field? Or the direction of the velocity, it's out of that page. What is going to be the formula? So out of the page, you can say positive Z. Or you can say up to the sky, because it's coming out, and if you put your page horizontally over your desk, you see it is directly coming out, it is toward the sky. And into the page, it means it's going directly into the screen, So this into, it could be field, force, velocity, or current. It doesn't matter. So when you see a cross, and beside of the cross, it's written B, it means the field is going into the page. If you see beside of the cross force, it means the force is going into the page. Into the page, in another word, we can say negative Z. Okay? This is so much important. Try to remember them. For the next section, we're going to use it for applying direction. Now, let's go for the magnetic flux. Guys, we have a magnetic flux. First of all, we had a magnetic field. Now, if this magnetic field being transferred or being passed through an area, the magnetic field lines that going through an area, in that case, it will produce something, we call it magnetic flux. So basically, magnetic flux, it is the number of the field lines passing perpendicularly, this is so much important, through a fixed area. So this magnetic field lines, it should go through an area. If it does not go through the area, there is no flux in that, over that area, or over that things. So if we have an area like this, now we have an upright area, and then we have a magnetic field lines going through that area. That's going to be the B, and this is going to be the area. So when you multiply the magnetic field with the area, you're going to have a magnetic flux. So we're going to use the letter phi for indicating magnetic flux. This letter stands for the flux. This is a Greek letter, phi. It's equal to what? Area times magnetic field. This is for finding magnitude. Okay? Area times magnetic field. A times B. So, you know, the unit of the A is what? Meter square, right? The unit of A is meter square. The unit of B is Tesla. So Tesla meter square, it becomes a unit of the flux, which we call Weber. Okay? So Weber is the unit of the magnetic flux. Weber, we wrote over there, which comes from Tesla meter square, and you can just simply say Newton meter per ampere liter. We will have them all. Okay? This is in chapter 6, this unit in electromagnetic induction we will have. Okay? Now, it is in the case, this A times B, it is in the case of having maximum flux. Why maximum flux? Because they are perpendicular. Highest amount of the magnetic field lines are going through that area. That's why it is going to be the highest one. But But if you have an area like this one, and you have a magnetic field over that area, like this magnetic field, as you see, no magnetic field lines is passing through that area. So in that case, if area is parallel to the magnetic field, so the flux is going to be equal to 0. So when the area is perpendicular to the magnetic field line, you're going to have a maximum flux. But when the area is parallel to the magnetic field lines, in that case, you will have a 0 flux because no magnetic field lines is passing through the area. We have this example. As you see, the area, and it's not making any angle, and it's perpendicular to that field lines, which is coming down those field lines. So in that case, we're going to have A times B. But in that case, because we have an angle, and we can apply the angle over there, no problem. In that case, as you see, we have, it's tilted. In that case, we're going to use cosine theta. AB cosine theta. But guys, there is something we have to understand that. We said perpendicular, and you know that perpendicular, the angle between the field and the area is 90. So cosine 90 is 0. Why we wrote AB cosine theta. And we said AB cosine theta, if the angle is 90 perpendicular, which is we said 90, it's going to be equal to the maximum. Guys, in this case, the angle that we take, we don't care about the angle of the area. We don't care about the angle of the area. We care about something, we call it area vector. It means the vector of that area. In another word, I can say face of that area. Have a look at this example, dear friends. Vector area is a vector. Magnitude is the area. The magnitude is the area, but direction is always normal to it. Look at this one. That's going to be the area. Isn't it this black line? It is normal to that area? Yes. So that's going to be the normal area. Now, in that case, what is going to be? If this blue line is magnetic field, what is the angle between the magnetic field and the area vector? Of course, 0, right? 0. Theta equal to 0 in that case. So when the theta is equal to 0, it means cosine 0 is 1. Cosine theta, which is the theta is equal to 0, cosine 0, it's equal to 1 maximum flux. Okay, maximum flux. Another example, keep it in your mind, we talk about the area vector. If the magnetic field is directly along the normal of the area, so the theta as shown, theta is equal to 0 in the figure. Look, the angle, in that case, the angle between area and the magnetic field is 90. But the angle between area vector and the magnetic field lines are 0. So in that case, we will say maximum flux. Look at this one. Maximum, we said angle should be equal to 0. Minimum flux if the magnetic field is parallel to the plane of the area, and the angle between the field and the normal to the area is 90, as shown. In that case, the flux is going to be equal to 0. Keep it in your mind. This note, we're going to use it in the next chapter. Look at this one. In that case, if this straight line shows the area vector, and this green lines, as you see, shows the magnetic fields. Magnetic field comes in that direction. What is the angle between the magnetic field and the vector area? The angle between magnetic field and the vector area is 0. Theta is equal to 0. So in that case, you're going to have a maximum flux. And logically, we see more magnetic field lines going through the area. But in the next one, in the part B, as you see, the green lines are going in that direction, and the area vector, look at the direction of the area vector. This is area vector. Area vector direction is to the up and it is perpendicular with the magnetic field lines, isn't it? This is the magnetic field lines, which is the angle between them is 90. That's why we said theta is equal to 90 and the magnetic field is equal to 0. I hope you understand the magnetic fields, and you have to know that if the angle between the plane of the area or area vector and the magnetic field is equal to 0, in that case you're going to have a maximum amount of flux. If the angle between magnetic field and the plane of the area, or we can say area vector, in that case the angle is equal to 90 perpendicular, so the magnetic field will be equal to 0. I hope you understand again. Now we have something about magnetic field of the Earth. Earth has a magnetic field similar to the bar magnet. When you have a bar magnet, of course, you will have the North Pole, South Pole. For Earth, we have this figure. If you could understand that figure, it will be perfect. In that figure, you have to know that this part of the Earth is the North Pole of the Earth, the North geographic of the Earth, right? And this part is South geographic of the Earth, South geographic of the Earth, sorry. South geographic of the Earth. But you know that for Earth, we have a magnetic field, and that magnetic field, it is not aligned with our north geographic pole. We don't care about this one. This is just geographic poles. Magnetic field of the Earth, due to the core of the Earth, it is the south of that magnet. It is near south of that magnet, near to the North Pole of the Earth. That's why if you have a north geographic, it means you have a south of the magnetic field of the Earth. And if you have a south of the geographic, you must have a north of the magnetic. So kind of vice versa. If you have a south geographic, you should have a north magnetic. If you have a north geographic, you should have a south magnetic. Okay? They are opposite. Why? We need to explain that one. In the chapter review, we have a question. In the question, it said if you have a bar magnet, you hang it up that bar magnet, okay? You hang it up that bar magnet, and in the bar magnet, we have a North Pole and South Pole. If you hang it up and rotate freely, that bar magnet rotates freely, can you use that magnet as a compass? Yes, of course. At the beginning of that section, we said a bar magnet, actually a compass is a small piece of magnet or a needle magnet, which is, it will be aligned with the magnetic field of the Earth. Now, if it is free to rotate that magnet, you know that South Pole will attract the North Pole. So north of that magnet will be aligned in this way. This is going to be the North Pole of that magnet and South Pole of that magnet. After a while, it will align itself with the magnetic field of the Earth. So the north of the magnet that I have, it will be attracted by the south magnetic field of the Earth. Somehow, or in another way, you can say the north of the magnet you have, it is the north of the geographic. That's why we use it as a compass. And south of the magnet that you have, it is going to be the south of the geographic. That's why we can use the magnet as a compass. If I could draw the figure of the Earth again, you can draw something like this. We call this is the North Pole. This is the South Pole. Inside the Earth, what do we have? We have a magnetic field. That magnetic field, it is going to be the south part of the magnetic field, south part, and that's going to be the north part of the magnetic field. And always the magnetic field is going to start to going from the north to south, and then like this. So if I have a magnet on Earth, in that case, the magnet is going to be aligned in this way. The north will be near to the south of the magnetic, and the south will be near to the north magnetic. In other words, this north, isn't it the north of the Earth? Yes, it is. So that's why I can use any magnet as a compass. I hope you understand this revision from the chapter 5, section 1. The most important one, let's do the sum up. The most important things you should know that is the magnetic field. Magnet cannot be cut. When you cut the magnet, poles are not going to be separated first. And the second one, magnetic field. Magnetic field, B letter, and it's a vector quantity. And then later we talk about magnetic flux. That's the symbol of the magnetic flux. That's the formula AB cosine theta. And then we said maximum flux when the area vector and the B are going to be parallel to each other. If the area vector and the fields were parallel to each other, when the theta between them is equal to 0, and theta flux is minimum or equal to 0, A vector is perpendicular with the field, so theta is equal to 90 degree. This is the most important things about this section. And we talk about the direction. I don't have to forget it, the last one, sorry, which is if we have a little dot, it means it is out of the page. If we have a cross, it means it is into the page. What do we mean into the page? It means negative Z, and out of the page means positive Z. I hope you understand. Have a nice time.